All right, I'm back with this problem. I had to stop for a meeting. I thought I could squeeze the whole problem in before it, but I couldn't. So remember, I just changed this page a little bit. So what we had done was this part. We figured out the diver hits the water at 2 seconds. So what I did to prepare for this was I just graphed a sketch of what it looks like, right? There's 2 seconds when the diver hits the water. There's 0 seconds when the diver is 32 feet above the water on that diving board, jumps up, gets to 36 feet at half a second, and then starts coming down, okay? So we were on part B when it asked us to find the velocity at impact. So the velocity at impact is the instant velocity when time equals 2 seconds. So at 2 seconds, what's the diver's instant velocity? Okay, so one thing I want to say is what we're doing here is we're trying to find the slope at t equals 2 seconds. So to find that slope, we're just going to pick another point, right, to find that rate of change. So I picked this point here. Like that would be the slope of that, between those 2 points. We could call this the distance between t equals 2 and to this point here. We could call that delta t, right? Some change in time. We're just trying to find the slope of that line. So what we would do there is we would be finding what we call the difference quotient. We would be finding, and instead of x, I'm going to write t. So f of t plus change in t minus f of t over change in t. And hopefully this looks familiar. This is just a slope formula, right? So this is y2, this point, f of t plus the change in t, minus y1 over the change in x, right? This is just slope. That's all we're doing. It's just using the variables we have. So let's find the difference quotient, right? What would it be? It would be, well, actually, before we do that, so I can find the slope of this line, right, this point. But what does it mean to have the instant velocity? It means we need the velocity at an instant. We need that interval to be infinitely small, right? We need that interval to get smaller and smaller and smaller and smaller. So what does that mean? We want the change in t to get as close to 0 as possible. So what we really want is to find the limit as delta t approaches 0 of this thing up here. Right? We want the interval to be so small, and if that interval gets small enough, the instantaneous slope will be, or the slope of the interval will be the slope at that instant of t equals 2, right? Because that interval, the change in t, is so small it's approaching 0. So we need to find this thing. So how are we going to find this thing? Well, first let's find this part. Right, let's do this first part right here, okay? So we're going to work on this part. Okay, so let's plug that in. This is your composite function, except we don't have s. Or f. I should have wrote an s of t because our function's an s, but you get the idea. So we are going to have negative 16 t plus delta t squared plus 16 t plus delta t plus 32. That's what that function equals when I plug that in. Okay, so now let's simplify that, right? This becomes negative 16 times t squared plus 2t delta t. I'm just expanding this, right? Plus delta t squared plus 16t plus 16 delta t plus 32. Now I can rewrite that as negative 16t squared plus 2t delta t plus delta t squared plus 16t. Whoops, I forgot my minus 6. This would be minus 32, right? I forgot to distribute. And then this would be minus 16 plus 16 delta t plus 32. Okay, so now that I've distributed that, can we get rid of anything? Let's see. We have I don't think we can, right? They're all different. We have, yep, they're all different. So that is what we have for ft of delta t. So I'm going to go to another sheet of paper. So now we just did this pink part. So now let's just evaluate the limit, right? I'm going to plug this in. Negative 16t squared minus 32t delta t minus 16 delta t squared plus 16t plus 16 delta t plus 32. All of that is take away f of t. So take away the original function, which is up here. I'm going to round a space. Minus negative 16t squared plus 16t plus 32. All of that is over delta t. Okay? Okay, now let's simplify more. Now I think I can get rid of some stuff, right? So I'm going to rewrite this without this negative there. All I'm doing is distributing that negative all the way through, right? Okay. Now, let's see what we can get rid of. If we can eliminate anything. So minus 16 squared and plus 16 squared go away. Plus 32 minus 32 goes away. What else? So we're left with minus 32t delta t minus 16 delta t squared. Oh, this plus 16 and this minus 16 go away, and then we have plus 16 delta t over t. Okay, let's rewrite. All right, now I'm noticing I can eliminate some of these delta t's, right? This delta t goes away, this squared goes away, that delta t goes away. So now I have 32t minus 16 delta t plus 16. Okay, so now I'm at the point where I can plug in as delta t approaches 0. So this whole thing equals 32t minus 16 times 0, because delta t is 0, plus 16. So this whole thing equals 32t plus 16. So what does? What were we finding? We were finding velocity at an instant. So the instant velocity, instantaneous velocity, is equal to 32 times t plus 16. Okay, so what is it at 2 seconds? Well, it's 32 times 2 plus 16, which is, did I forget a minus somewhere? Oh yeah, I did. See this minus? Oops, I was like, that answer is not right. Forgot to carry over that minus. So negative 32 times 2 plus 16, which equals negative 64 plus 16, which equals negative 48 feet per second. Okay, so the instantaneous velocity when that diver is hitting the water is negative 48 feet per second, right? So all of that was to find the instantaneous slope at t equals 2, which we did by finding the slope of an interval and narrowing that interval until it was 0. So let's do this last part. When does a diver stop moving upward and start their descent? Well, I can look at the graph, right? When does the diver stop moving upward? Well, it's at the peak here, right? You can see the turnaround point here is at half a second. So that is when, so I know, I'm just going to write here, I know it happens at t equals 0.5 seconds. But how do I know that, right? This is when the velocity is 0, right? The turnaround point. And you can see what would the slope of that tangent line at that point be. That slope would be 0 because it's a max. So if you want to figure that out mathematically without a graph, you have the equation for velocity. We figured it out. It's right here, negative 32t plus 16. So if velocity equals negative 32t plus 16, and the turnaround point is when the velocity is 0, I'm just backwards solving for t, which means t equals 1/2, right? Which is what we figured out from looking at the graph. Okay, so some notes we want to take here are the average rate of change, this is just the slope. But if you want to find the change in an instant, you need to narrow that slope. You need to narrow that interval, I mean. So the only way to narrow that interval until it's so small is to take the limit as what we did, I'm going to write it how we did it, was as delta x goes to 0 of f of x plus delta x minus f of x, just replacing our t's with x's. What we did was take the limit as delta x approaches 0 of the difference quotient, or the slope, right? Or this is also the slope. We took the limit of the slope as the interval gets closer to 0. Sometimes you will see this written as, another way you'll see the notation is the limit as h goes to 0 of f of x plus h minus f of h over h. It's the same thing. H is just equal to the change in x. I don't know why you see that sometimes, right? So we narrow that interval, so we have to take the limit. Okay, so this was about learning what the derivative means in context, right? We've learned that the derivative of a position function is the velocity function, okay? This is the derivative. And tomorrow, or the next day we have calculus, we are going to turn this into the formal definition for a derivative. So I know it seems a little wonky. You get some practice. We'll do it again tomorrow, and it'll all feel better, I promise.